Next, we're going to look at partial derivatives of functions. Partial derivatives. And we use partial derivatives when we have more than one independent variable in our function. So let's say you're given a function. Let's say it's a function of two variables, x and y. Then if we have df dx, this symbol looks similar to delta, but it isn't exactly a delta. It's a little bit different. But this symbol represents the partial derivative, which means you have more than one variable, but you're taking the derivative with respect to one of those variables. And so it can be represented df dx, or it can be represented by f with a small x here. And this means derivative with respect to x while holding all other variables constant. This means the derivative with respect to x while treating all other variables in the equation as constants. Again, it can be df dx or f with a small subscript of x. And then we have df dy, or this can be f with a small y, and this is the derivative of our function with respect to y while treating all other variables as constants. So those are the two derivatives. If we have just two independent variables, x and y, we have these. So we're actually going to do some examples next. So let's say we're given this function. And we're asked to find df dx and df dy. So again, let's do df dx. And again, we're taking a derivative of this with respect to x, but we're going to treat everything else, any other variables, as constant. So again, let's go through, take the derivative, bring the 4 down. That's going to be 4 times 3, which is 12x cubed. Now the derivative here with respect to x, I'm going to bring the 2 down. That's going to be minus 4x. And then y just comes along for the ride because it's just a constant. It would be almost the same as though you had like a 5 here and you took the derivative. And so it's just coming along. And now take the derivative of this. Now notice that this is constant, the 3 is constant, this is y, it's not x, so we're going to treat it as constant. So this whole thing, this whole term really just made up of constants. And of course, if we're taking a derivative of a constant, that's always just going to be 0. And of course, the derivative of this constant here is also 0. Now, normally you don't have to put the zeros in, so you could actually just write it this way. Remember, we're taking derivative with respect to x, but treating everything else in the equation as constants. So let's do the same thing, df dy. We're going to take the derivative with respect to y, treating everything else as constants. So go across here, the derivative with respect to y of this, again, we're treating x as constant this time, so that's just going to be 0 because there's no y's at all there. Derivative of this with respect to y. Remember, this is almost like numbers being multiplied by y. So it's y to the first power. So this is almost like a constant times y. And the derivative of that would be just that constant. And derivative of this with respect to y, bring the 2 down. And of course, the derivative of the constant is always 0. Once again, we really didn't need to put those zeros in. I just put them in just so everyone could see clearly what we're doing. And we get this. Let's do another example here. Let's say we're given this function. Find fx and fy. Remember, this just means the same thing as df dx. This is the same thing as df dy, but I just want to put this down because when you look at books, sometimes you can see either one. And so again, let's do f of x. Again, let me just rewrite to remind us it's the same thing as df dx. So we take the derivative of this. Now, we have this to a power. We have a function to the power. So we'll have to use the chain rule. And remember, the chain rule, you would sort of, you can think of covering this up and bringing the 4 down. And subtracting 1. So it's almost like this is like an x. You bring the 4 down, subtract 1 like this, and then the inside stays the same. And now we're taking derivative with respect to x only, so that means we're treating everything else as constants. So when we take the derivative of the inside next, from our part of our chain rule, we're going to be taking the derivative of this with respect to x. So this is almost like a constant and a constant times x. So the derivative of the constant times x is just a constant. So it's going to be 3y cubed. And the derivative of this with respect to x, once again, we have like minus 4 is a constant, y is a constant, so we're going to be just left with minus 4y, like that. So now let's do the derivative with respect to y. And just to remind ourselves, fy means the derivative of the function with respect to y. Again, we're holding everything else, any other variables, as constant. We're treating them as constants. So again, going back to here, bring the 4 down. And subtracting 1 again. Remember, I'm going back up here, bring the 4 down, subtract 1 for the exponent inside the same, but then it's a chain rule, so we take the derivative of this next with respect to y. That means we're going to treat x as constants. So again, bring this down, that's going to be 9xy squared, subtract the 1. Then over here, again, x is constant, so this is like a constant times y. Derivative of that is minus 4x. And there we have it. And let's do another example. Let's do this one here. So let's take a look at this problem. Now again, this time we have the product rule. We have two functions multiplied together, or actually several functions multiplied together. You could treat this in a couple different ways. You could probably treat this as, this being one function here, and then this being another function. So let's take a look at this. So if we want to do df dx, it's a derivative of this with respect to x, holding everything else constant. So we'll, again, treat it like as a product. So we're going to have the derivative of the first, and the derivative of this with respect to x would just be, this is almost like a constant times x, so derivative of that would just leave us with a constant. So derivative of the first times the second function plus the first times the derivative of this function. And now, so this one, of course, is going to be e to this times the derivative of this exponent. So I don't know which order you want to put them in. Let me put this like this. So we know that e is always going to be there with this exponent. Remember, whenever we take the derivative of e, and this is is a variable, it always remains. And then we take a derivative of what this exponent is with respect to x. That means we're going to hold everything else constant. So derivative of this exponent will be 2xy squared. And then the derivative of this with respect to x is just going to be minus 3. So there we have it. So just double check that. again, we took the derivative of the first function times the second plus the first function times the derivative of the second. Again, this is going to be e to the power times the derivative of that exponent with respect to x. So it'll be 2x y squared minus 3. Now take df dy. Again, going back to our original function here. Again, we'll treat it as a product rule. Derivative of this with respect to y, treating x as a constant. That'll bring the 4 down. That'll be 4x y cubed times this. Plus the first function times the derivative of the second. Remember, the e to the power, if there's variables there, that's not gonna change. Then the derivative of that exponent with respect to y. So with respect to y, we'll have what? 2x squared y then minus the derivative of this, but that's just going to be 0, right? Because we're taking derivative with respect to y, that's just going to be 0. So we can just leave it like that. Now, of course, these two, we probably could have combined terms a little bit, make them look a little bit nicer. If you like, you could have multiplied these through. But right now, I just kind of want to illustrate how to take the derivative. And let's do another one here. Let's consider this function. Let's say we have maybe 4xy plus 3x squared y times the log, natural log, of 4y squared plus 5x squared y, like this. So let's take a look at this one. We want to find df dx and df dy. So let's take a look at this one. Again, we have a product again. And again, take the derivative with respect to x first. Again, so we can consider these two functions, this one times this one. So the derivative of this with respect to x will be right here. This is going to give us what? 4y plus derivative with respect to x is going to be 6xy times this. So it's derivative of the first times the second, then plus, I'm going to need more room, so I'm going to put this down here, plus the first times the derivative of the second, which is this one here. So it's going to be the first times the derivative of the second. Now remember, when you do the log, the derivative is always 1 over the argument, whatever you have here. 1 over that argument for y squared 5x squared y times the derivative of that argument with respect to x. Now, we take the derivative of this with respect to x, that's just going to be 0, because that's like a constant, so it just goes away. And then over here, with respect to x, what's that going to be? 10xy. So I think I'm going to run out of room on my paper here, so I'm going to have to go to a next page to do the next derivative. Let's do the next one here. I'm going to do df dy. In fact, let me move this up a little bit so we can see this. So df dy, derivative of this with respect to y now. Again, the derivative of the first could be 4x plus 3x squared. Notice, because this is like a constant times y, so the derivative of that with respect to y is just going to be 4x, the constant. This is like a constant times y, derivative of that will be just a constant, times the log. So derivative of the first times the second plus the first times the derivative of the second. Once again, it's 1 over this. One over that times the derivative of the argument, which again, with respect to y, bringing this forward, that's going to be 8y plus 5x squared, like this. And so take a look at those derivatives. Again, this is a product rule, but again, for this one, we treated everything else except x as constant. For this one here, we treated everything but y as constants. Next, we're going to take a look at higher derivatives. So we're going to talk about the second derivative with respect to x and the second derivative with respect to y. The derivative with respect to x twice. Holding other variables constant. or treating other variables as constants. And then, of course, this is the derivative with respect to y twice, treating other variables as constant. And again, there's no real mystery on these kind of problems. If you understood how to do the first derivatives, you could understand these pretty easily. They can sometimes get messy if the equations are real big, but there's nothing really unusual about them. So let me just go through a few here. So let's consider this. And let's find, again, we can use either notation. Sometimes this simpler notation is a little bit easier to work with. It all depends. But let me do it this time. So let's take the second derivative. Again, this is the second derivative with respect to x, second derivative with respect to y. And that's usually how these are called. The second derivative with respect to x, second derivative with respect to y. And let's go through it. Now, of course, what we have to do, we have to find the first derivative first. And so let's take the first derivative with respect to x here, treating y as a constant, with that going to be 9x squared y. And then 8xy squared plus 7. And this is 0 and 0. And we're going to take the next derivative with respect to x. So what we do when we take the second derivative, we look at the first derivative and take the derivative of that. And bring this down. Again, that's going to leave us with 8y squared, and that's going to be 0. So take a look again at what we did. We took the derivative with respect to x first, and that gave us 9x squared, 8xy squared. This came to be just 7, 0, and 0. Then we do the second derivative. We look at the first derivative and take the derivative of that. So that was 18xy. Again, it's still with respect to x. And then this one, this is once again like a constant times x. So we're just left with a constant. We have that. So let's take the second derivative with respect to y. So first we need the first derivative with respect to y come up here. That's going to be 3x cubed. And over here, this is going to be 8x squared y. Then that's going to be 0. And that's going to be minus 3. And that's just going to be 0. Now we want the second derivative. And that's going to be again, the derivative with respect to y of the first derivative. So this is going to be the derivative. That's really just like treated as a constant when we're taking with the derivative with respect to y. So that's 0. And then over here, this is like a constant times y. So we're just left with the constant. And of course, the derivative of a constant is 0, and we get that. So again, took the first derivative with respect to y. And then 0 minus 3, then took the second derivative. Again, we go back to the first derivative, take the derivative that with respect to y, that's 0, 8x squared, and 0 like that. Again, like I said, when the functions get bigger and you have like a lot of product rules and quotient rules, these derivatives can get very messy. However, the main process is exactly this. Take the first derivative and take the second derivative. So again, this one here is called the second derivative with respect to x. This is called the second derivative with respect to y. Now we have another category when we're dealing with partial derivatives. That's going to be mixed partial derivatives. And that's when we take the derivative with respect to x first and then y second, or we take the derivative of y first and x second. So let's take a look at, first let's take a look at the notation. And so when let's say we take the derivative with respect to x first, and then we take the derivative of that, it would, with respect to y, it would look something like this, or the actual, the way it's usually actually written would be like this. Now, again, we have to kind of be careful of our notation. Again, it's usually going to be like this, or like this. Now, notice, don't get confused about this, but they're in a different order. This means when you have this notation, this means derivative x first and y next. And again, the reason it's in this order is because you're first taking a derivative with respect to x, and then taking the derivative of that with respect to y. So you end up in kind of reverse order. When we use this notation, we have it in the direct order, derivative with respect to x first and y second. Let me write that down. Derivative with respect to x first then y second. So when you're asked to do it, you'll be asked to either do it in this form or be asked to do this. And now going the other way, let's say if we first take the derivative with respect to y, and then we want the derivative of that with respect to x, we take the derivative with respect to y first, then x, then that's going to be written dx dy. like this, or like this. Both of these mean y first and x second, y first, x second. This. Let's do an example again. I'm going to do relatively simple examples, but the same method will apply no matter how difficult or how extensive your equations are. You still follow the same ideas. So let's actually just pick an example here. And let's say this is going to be x squared y to the 5th minus 6 y squared minus 2x plus 5y plus 9. And let's find all the derivatives: fx, fy, fxy, fyx, fxx, fyy. Let's take a look at this problem here. So derivative to this with respect to x is going to be 2xy to the 5th. Derivative of this with respect to x is minus 6y squared. Derivative of this with respect to x is minus 2, constant and constant. And let's take the derivative of our function with respect to y. This is going to be 5x squared y to the 4th. This is going to be minus 12xy. That's going to be 0. That's going to be 5. Like this. And let's do some of these other derivatives. Let me do this one here. Fxy. And this is do x first, then y. And let me write it down here. Now, let me actually write the other notation just to remind us that if we were asked to do the other notation, it would be the opposite, dy dx, like this. Again, this is saying do derivative with respect to x first and y. So we have to go back to this one and take the derivative with respect to y. So it's saying we're going to go back to this, take the derivative with respect to y. So it's going to be 10x y to the 4th. Then this is going to be minus 12y. Of course, that's going to be 0. Now let's do this one here. Fyx. I think I'm going to run out of room, so I won't put this here, but that'd be the same as if we were asked to do this one here. So that means we're going to go back to this one, do this one first. which we did, do y first, and take the derivative with respect to x of that. So again, let's bring this down. It's going to be 10x y to the fourth. And then the derivative with respect to y here will be what? Minus, excuse me, with respect to x we're doing, minus minus 12y, and that's 0. So again, do y first, which we did, then take the derivative of this with respect to x. Look at that. Now notice that fxy came out the same as fyx. And later we'll talk about that. But if your functions are continuous and your derivatives are all continuous, there's a bunch of conditions. These are going to be the same. In fact, probably most of the functions you deal with, fxy will end up coming out the same as fyx. So unless you have a crazy function, a function is discontinuous, or some of the derivatives don't exist in certain regions, these are going to be the same. So finally, we want to do the fxx. That means we go back to this one, take another derivative with respect to x. So it's going to give us 2y to the fifth. We take the derivative of that with respect to x. 0, 0. I guess that's all we have. Then over here, fyy. Go back to this one, take another derivative with respect to y. That's going to be what? 20 x squared y cubed. And then over here with respect to y, it's going to be minus 12x, and that's going to be 0. So just double check everything. We took the derivative of this a second time. We did x first, then did it again. And notice these were both 0, and we just had 2xy to the fifth. Over here, we did another derivative with respect to y, 20x squared. We brought the 4 down, gave us y cubed minus 12, like that. Again, more complicated functions, especially if you have products or quotients or exponents, these get much messier, but the process is always going to be the same. This notation up here, or this notation, means x first, then y second. Over here, this means y first and x second.